All right, guys, so some classes didn't get a chance to finish up example 2, so I'm going to do that first. I think all of us got to the point where we found the derivative using the chain rule, and we talked about the fact that rewriting it as a fraction is a good idea because that means when you're finding where the derivative equals 0, you can just set the top equal to 0, and when you set where you're finding places where the derivative does not exist, you can just set the bottom equal to 0. One thing that I just want to make sure that you understand that I did is I distributed this 1/2 to this part here, and so that's why there's no 2 on the bottom down here, and why the numbers on the top changed up there, okay? So you can do that, you don't have to, it doesn't really affect your solving. So if I go ahead and figure out where does 2x cubed minus 3x equals 0, my hope is that you feel comfortable going ahead and factoring out an x. So you have 2x squared minus 3 equals 0. That means I have possibilities of x equals 0, or 2x squared equals 3, or x squared equals 3/2, and then solving for x, I do get 2 answers, right? Plus or minus the square root of 3/2. Since there is no domain restrictions, remember that, I have all of these as a possibility. Okay, so far, 3 critical numbers. Now I'm going to turn my attention over here. Okay, I'm looking for where the bottom equals 0. That would be the same thing as x to the 4th minus 3x squared plus 4 equals 0, since I could just square both sides to get rid of the square root. Okay, one thing I do want to kind of point out to you is that you might be able to solve this algebraically. People were talking about making a u substitution, like using u for x to the 4th, and you can do that. I do feel like this is a calculator question anyway, and so at this point, I would have you get out your calculator, take a look and put this in y1, and then see where does it hit the x-axis, okay, because that's be places that it equals 0, and you guys know how to find those with your calculator. Okay. So if you do that, the magic of this video, right, I can do this for you. This is what you would see on your calculator screen, and what happens is it never touches the x-axis at all, and so when would this happen? Never. Okay, so we don't get any critical numbers from when the first derivative doesn't exist. So basically, I'm at the point where I know I don't have endpoints to check, so I'm either picking the first derivative test or the second derivative test, right, to go ahead and prove where there's maximums and minimums. Okay, and so what I would say to you is, if I think about the flow chart we've been talking about, are all of my critical numbers from places where the derivative equals 0? Yes, right? And so then the next question I ask myself, is the second derivative easy to find? And I would say, not even a little. Right, and so I do not think this is a good candidate for the second derivative test. I think we're talking about the first derivative test. So I'm going to go ahead and create my sign chart for the first derivative, putting my 3 critical values, okay, on my chart. And I think that it hopefully makes sense to you that this would be a good calculator problem, because I don't know about you, but I don't really know too much about the value of the square root of 3/2 off the top of my head. So go ahead and put that in your calculator, right? And then you can pick out some good testers once you know what that is, and they probably look like that, okay? If you are already allowed to use your calculator, this would be a good time to practice, okay? And this is what I would do. I would put this version of the derivative into my y1, okay? And I wouldn't pick the version where we traded it to a fraction, because you have to make sure you put in all the correct parentheses, and I think a lot of us are going to make mistakes on that. Okay, so if you put that into your y1, you can go to the table and just look at your tester values and see, does it give you positive or negative numbers in the y column, right? And again, all you care about is positive or negative. Okay, and so I would practice doing that right now and verify that you do get negative, positive, negative, positive. Okay, according to the first derivative test, when I see a change in sign of f prime from negative to positive, that tells me that there is a relative minimum, which I am interested in, right? When f prime changes from positive to negative, I see that there should be a relative max in this case, I guess, the distance, right? And negative to positive in d prime would be a relative minimum. Okay, so don't care about this because I'm trying to minimize that distance. I care about those two places. Should it be surprising that there's two places where there's minimums? And I would say no. If we look back up here, since the graph of 4 minus x squared is symmetrical about the y-axis, right? If I find this distance here, well, then there's going to be a corresponding point over there. Okay, to actually come up with the ordered pairs, I need to plug those x values back in and get y values. Good news, right? I already know an equation for y. It's 4 minus x squared. And so all I have to do is go ahead and plug in my two critical numbers that give me relative minimums. Okay, in this case, the nice thing that happens is it cancels out the square root. And so I would have 4 minus 3 halves. Well, 4 has 8 halves in it, so 8 halves minus 3 halves is 5 halves. Okay. And similarly, if I plug in the square root of 3 halves and square it, I get the same thing. Okay. Remember, my very final answer is a sentence, right? So if I'm, basically I'm going to say the points on y equals 4 minus x squared closest to the order pair 0, 2 are negative square root of 3 halves, comma 5 halves, and square root of 3 halves, comma 5 halves. And that would be my final answer.